Perfect.
All right. So, hello everyone. Thank you all for assisting my thesis defense entitled Toward Reliable and Bounded Latency for the Internet of Things. The goal of this presentation is to present several multipath algorithms, multipath routing algorithms in order to improve the transmission reliability in IoT devices. To do so, I decided to divide my talk in 5 parts. First, I will do an introduction of the problem statement in chapter 1. Then, in chapter 2, I'm going to talk about the patterns and tools used in this investigation. After that, in chapter 3, I'm going to talk about the several multipath algorithms that they were performed here, where I'm going to show their performance evaluation in chapter 4. Finally, I will conclude my talk in chapter 5 and giving the pertinent conclusions. So to begin with, first I will do a quick talk about the history of the revolution of the industry. In fact, since the first steam engine was created, the humanity have been passed through 3 big industrial generations, and right now we are moving on to a 4th one denominated Industry 4.0. So in the first generation, the basis of the mass production settled down, leading the craftsmanship left behind, and people starting to migrate to the big cities. Then, in the second generation, the factories is starting to adopt fossil fuel in order to make more powerful and faster machines in order to improve their productions. One important fact here is that the electricity also starting to be developed in this generation. Then, in the third generation, we're starting to use computers, leading the industry to work with softwares to make their automatic process. And right now we are passing through the 4th generation denominated Industry 4.0, where the main idea is to let machines to work with digital tools so they can recopilate data in real time to make their own decisions by using smart algorithms. So what is behind about this Industry 4.0? Well, as we can observe here, there are many terms that right now there are hot topics in the industry, such as machine learning, big data, nanotechnologies, and many more. But in this work, we are going to focus specifically in the Internet of Things, or IoTs. So how we can define the IoTs? Well, in the documentation, there are many definitions since it's a really abstract concept. But in general terms, it's a set of standards developed to connect several sensors devices into smart networks. One important fact here is that the IoTs follow a best effort principle, meaning that integrate them to the industry is really challenging, given that the industry requires quality of service. So now that I already talked about the basis of the IoTs, I'm going to move on to some of the technologies that they are within them. So first of all, we have the low power wide area networks, or LP1s, which in fact consist in a group of devices that they can perform long range communication. On the other hand, we have the wireless sensor networks, or WSNs, which consist in a group of devices that they are characterized to perform low range communication or short range communication. So even though that these two type of technologies are opposite between them in their characteristics, both of them they belong to a big group within the IoTs denominated low power and lossy networks. And these low power and lossy networks possess many characteristics, such as they have low data rate transmissions, given that um, they have asymmetric links. Also, they have restricted power reservoirs, given that many of these devices perform with batteries for their power supplies. And lastly, in terms of reliability, given that they have asymmetric and lossy links, their performance is not pretty well in terms of transmission reliability. However, even though that these low power and lossy networks, they have limitations, they also have advantages. In fact, if we compare the prices of these devices with the rest of them in the market, these ones are really cheap. Also, they are easy to deploy since many of them support many of the operating systems that are within the IoT networks. And lastly, and most important, is that these devices are open source, meaning that they don't require a specific license to work with them. This leads us to the distribution that have these networks. So starting with the star topology, this one first is a network distribution where several nodes transmit to a specific node, denominated base station or central node. And these ones are normally used by the LP1 technologies, given that their long range communication allow them to perform single hop transmission. Then we have the mesh topologies, which is, in fact is a type of networking where all the nodes cooperate in order to transmit their information. And these ones are normally used by devices that they can perform short range communications, as I explained with the WSNs. In fact, at the time that a packet have to be transmitted, these ones have to pass through several nodes until this one reaches to a specific target. And the path that this packet took to reach to that target, we are going to denominate it routing. And as we can observe in the example, routing can be performed in different ways to reach to that specific destination, but it has to go according to the required needs of the network. This leads us to the routing protocol in study RIPL, which is a distance vector routing protocol for the low power and lossy networks. In fact, this routing protocol is characterized to work with any type of technology, given that does not rely on other network layers. And most importantly, its philosophy is convert a typical DAT network, as we can observe in this example, to an optimized DODAC network. To do so, this protocol directs all the routing efforts to a central node denominated DODAC route. However, even though that this routing improves the transmission reliability, its single path behavior is not enough to satisfy the quality of service requirements of the industry. And this is mainly because as more hops a packet required to reach to a specific target, higher is going to be the probability that this packet is going to get lost. And this behavior can be followed by the following binomial distribution that we can see in the current slide. In response to that, we decided to extend RIPL with multipath, since its behavior does not affect the RIPL functionality. And as we can observe here, also multipath provides many characteristics, such as path redundancy, meaning that many paths can merge into specific points, providing transmission stability. They also provide path diversity, given that in a wireless network, not all the links will have the same quality for do the transmission. And finally, they also can provide delay performance, given that, as I mentioned before, routing can perform in different ways, meaning that a different route can perform in less hops than the original path. So in what things multipath RIPL have been used? Well, there are many investigations about this subject, but in this presentation, I'm going to present just 3 of them. In the first place, we have the one denominated load balancing, which consists in distribute the traffic load in some of the nodes that possess overload traffic when a transmission is performed. To do so, this implementation, what normally does is distribute that traffic to other nodes in order to reduce the traffic load of that specific nodes. Then we have the broadcast implementation, which consists in enable the broadcasting transmission around the nodes. In this case, given that there are some methods in RIPL that they just can provide upward communication, the broadcast communication allowed the downward communication, providing broadcast transmission, as we can see in this example. And finally, we have the transmission reliabilities implementations, which consist in copy the same amount of traffic that is performing by a default single route through many routes in order to increase the probabilities that that packet can reach to that specific destination. However, even if this is if we don't have a smart enough way to replicate this data, then the multipath implementation can produce flooding inside of the topology, making making having a really big waste of energy in terms of transmission. Given this, in this presentation, we are going to focus specifically in different strategies to create the multipath algorithms in order to perform the transmission reliability in Ripple networks. Now that I finished with chapter 1, I'm going to move to chapter 2, where I'm going to talk about the patterns and tools used in this investigation to improve the transmission within the multipath algorithms that I'm going to present in chapter 3. So starting with the multipath pattern, this one is a set of specific path states where their goal is to merge in certain points in order to improve the forward transmission. And in this presentation, I'm going to present two of them. The first one, denominated disjoint pattern, consists in generate several parallel paths starting from the source node and merging all of them specifically at the target node or root node. To do so, the relay nodes that are between the source node and the target node are going to perform a single path. And in this way, we can create a disjoint pattern transmission. Then we have the braided pattern, which in fact consists in allowing the source node and the relay nodes to have an alternative path to perform their transmissions. To do so, an alternative parent is going to be selected in order to create this alternative path. One important fact that we have to consider here is that that alternative parent requires at least one node in common with the preferent route in order to make their selection. Now we are going to pass to pareo, which in fact are a set of functions in order to improve the transmission forwarding of a specific packet in the multipath algorithms. So starting with the first function denominated automatic repeated request, this one have the goal to perform a limited number of retransmission each time the receiver does not receive a specific packet from the transceiver. To do so, at the time that the transceiver will send a packet and this one is received by the receiver, then the receiver is going to send an acknowledgement packet as response. So in the case that this acknowledgement packet is get lost or not get received by the transceiver, then the transceiver is going to retry it again. But what makes difference about this function and a normal retransmission implementation is that this one possesses a set of predefined number of retransmissions, meaning that if a transceiver retries reach a specific threshold of retries, then it's going to stop retransmitting. Now let's move on to the next two functions, replication and elimination. In fact, the goal here is to create several packet replicas in order to transmit them in several paths, as we can see in the following example. To do so, the source node set a unique ID to the packet and its copies in order that make identify them along the transmission networking. In this way, we can create several replicas that are going to be transmitted in parallel to make more attempts of transmission to that specific packet. Additionally, as the title said, also provides an elimination method, which consists in dropping all the delayed replicas that a node receives. Meaning that if I receive already a replica with that specific ID, then the other replicas are going to be dropped in order to release the traffic load of that specific node. By last, I'm going to talk about the overhearing implementation, which goal is to allow multiple parents to receive a unicast packet by taking the advantage of the wireless coverage. But this implementation are only going to be used by the selected parents that are going to perform the multipath transmission. So to make a quick resume, all these functions are used to improve the transmission reliability. However, these ones can work independently and they don't require from the other functions to work with. This leads us to the next chapter, where I'm going to talk about the several multipath algorithms that they were developed in this thesis. To do so, I decided to divide this chapter as follows. In the first place, I'm going to talk about the end disjoint algorithm, which in fact take the basis of the disjoint pattern that I explained before in order to create a multipath algorithm in REPL. Then we have the common ancestor algorithms, which consist in a set of algorithms allowing the nodes to perform and to search a specific alternative parent by using braided pattern strategies. And by last, I'm going to talk about the on-demand selection, which consists in a strict braided selection for the multipath transmission in order to optimize the total number of relay nodes when a packet is when a transmission packet is performed. So to begin with, the end disjoint pattern, as I mentioned before, consists in allow REPL to behave as multipath, taking the characteristics of the disjoint pattern. And to do so, this algorithm implement the packet replication function in order to produce several replicas, and these replicas are going to be distributed along the several paths created by this algorithm. It also enabled the retransmission, given that several devices that perform between the source node and the root node are going to perform in a single path. So with the retransmission, we were enabled to allow the packet to have more chances to be forwarded. But one important thing that we have to understand is that we are using REPL as our routing base, given meaning that having a specific strict disjoint scenario is not realistic and just brings complexity to the implementation. To do so, we established two types of strategies for that selection. First, the one denominated basic strategy allowed the path merging across the topology. In this way, we can allow in the normal parent behavior of REPL during this transmission selection. However, as we can observe in this example, only one, if several replicas are merging a specific point, only one replica is going to be forwarded, leading us less attempts to make this replication go through the target node. Given that, we implement the second strategy denominated advantage, which in fact improves the previous method, but allowing the merging point to recreate the same amount of replicas as replicas received by it. In this case, we can observe that our node D is the merging point, then it's going to replicate the same amount of replicas as the ones that receive it. In this case, they're going to be 2. So as response, what we get here is that we can improve the probability that all the replicas gets to that specific target. Now I'm going to move on to the common ancestor selections, or the CA and the CA selections, which consist in 3 types of multipath algorithms. And the idea of these alternative parent selections, these common ancestor selections, is to find a specific alternative parent to provide the multipath algorithm. To do so, we are going to move on to the following scenario, where two relay nodes perform the same preferent parent. That in this case is going to be D. So in this case, as A is the preferent parent of S, then to select a strict braided pattern, S is going to select node B as its alternative parent, making the strict CA selection. Then we are going to move to a similar scenario where, as we can observe here, our target preferent ancestor D do not have the same, do not have, it's not the same preferent parent for node B, given that B is merging its preferent parent with E and with C. However, given that D belongs to the parent set of B, then we can perform a medium CA selection, allowing node B be selected as the alternative parent of S. And lastly, we are going to move to the following scenario, where, as we can observe, there is no related path to D from the parent from the nodes B and C, leading us to not perform strict CA selection or medium CA selection. However, given that the preferent parent of S possess in its parent set the same node of the parent set of B, then B can be selected as soft CA, as we can observe here. So how different is the variance of finding an alternative parent by these algorithms? Well, it is reflected here in the following 3D plots. As more strict is the CA, less is going to be the probability to have an alternative parent. However, if we get a bigger probability of having an alternative parent, then we can replicate this packet even more, improving more the transmission reliability. But also this have a disadvantage, given that as more nodes I'm using, more is going to be the power consumption. So we have to be really careful about what type of selection we are using in a specific topology. Now I'm going to move on to the last algorithm, denominated on-demand selection, or Odyssey, which consists in minimize as much as possible the power consumption while in parallel guarantee a full braided pattern to improve the reliability. To understand this better, I'm going to move back to one of the common ancestral algorithms that I presented before. So as I explained it before, strict CA to have an alternative parent requires that the two relay nodes that are above the source node requires to be and they need to have the same preferent parent. However, given that strict CA does not care about what alternative parent is created, we can have alternative parents that can expand this type of selection. And as we can observe here, given that the two siblings nodes that are above the source node, they possess different alternative parents, then the path is going to be replicated, and we are going to create flooding, as we can see in this example. So Odyssey instead avoid this behavior by letting the siblings nodes that are above the source node to have the same preferent parent as equal as the same alternative parent, as we can see in this example. As a result, we can obtain a strict braided pattern, reducing as much as possible the number of of parents used to perform the transmission. So, in order to make this algorithm work, first of all, when we create this pattern, first we are going to do a medium CA strategy. And the reason of that is because with a medium CA strategy, we have more chances to find an alternative parent than in a strict CA method. Then the node that is going to possess this, that is going to transmit the packet, in this case, in the source node S, is going to focus its its eyes specifically to the preferent parent node C to recopilate its preferent parent and alternative parent. And what is the reason that it's doing that? Well, then at the time that this source node is going to transport this packet, then the relay nodes are going to receive the information that this packet sent with the transported addresses of the preferent parent and alternative parent of C. So then these relay nodes are going to compare their parents selected with the transported parents, and if everything is okay, we can make sure that we have a strict braided pattern. Then if everything is okay, those nodes are going to proceed to recreate the same cycle as the source node until the packet reaches to that specific destination. But what happens if the relay node possesses a preferent parent that is not matched with the transported parents that are carried in the data packet? Well, if it is that the case, then in this case, B is going to save its preferent parent in auxiliary box, and is going to set the transported parent as preferent parent. In this case, we can recreate again a strict braided pattern as we can see in this example. Then, as we can see in this example, then we are going to select also the transported alternative parent that is carried in this packet, and we will complete the full braided pattern, the strict braided pattern selection. After that, the full cycle start again. Then the node that changed its preferent parent to with the transported preferent parent is going to remove that transported parent to the specific to the previous preferent parent in order to avoid bad behavior of the REPL instance. And then all the values are going to be restored. By last, if the transported packet do not satisfy with any option, then the relay node is going to keep its preferent parent. And if there is no alternative parent to that specific node, then a soft CA strategy is going to be used. After that, all the packets are going to be transmitted, then the full Odyssey cycle is going to start again. So after all this analysis, what is the profit of this methodology? Well, in our simulations, we demonstrate that independently what type of topology scenario that we have, in the vast majority of the case, Odyssey will always going to have 2 relay nodes per hop. In addition, given that we are using a strict braided pattern for the path selection, we are expecting a really high reliability and transmission reliability. This leads us to chapter 4, where I'm going to talk about the performance evaluation of each algorithm. But first, I'm going to talk about first the topology that it was used in this work. So the type of the scheduler that we use is denominated TACH, and is one of many scheduling protocols for the MAC layer. And its main characteristic is to divide time into time slot, and at the same time divide frequency into channels. So in this case, in this way, we can make sure that in a specific gap of times, we can perform a transmission and a reception during the transmission action of a packet. In the first case, as we can observe in green, this slot is going to be specifically for beacons, meaning that this slot is specifically to make the nodes join to that specific network. Then, in the slots that we are going to have with clear blue are going to be used specifically for the control packets of Ripple. And these ones are going to, one of a specific thing here is that they are going, and these slots are share slots, meaning that they can be used even for any type of control packets of Ripple, meaning that they can perform a single path or broadcast transmission. Then we go to the dedicated cells, where the cells that are in blue are going to be specifically for the data transmission, and the cells that are in orange are going to be specifically for receiving transmission. So as we can observe here, the ACH allow us to specify, as I mentioned before, the time that I'm going to do a transmission and the time that I'm going to do a reception. Then we have the purple slots that they are going to be specifically for retransmissions. In fact, in our scheduler, we are just going to perform one retransmission into the full slot frame in the scheduler. And finally, the yellow slots are going to be performed just for overhearing. So in this way, this method is going to be repeated, and this slot frame is going to be repeated until the full lifetime of the network life. Then we have the parameters used in this investigation. As we can observe, we use a total of 32 nodes, where we provide one specific node for transmission and 6 hops in order to perform that specific transmission. Also, the nodes that are in each specific slot can communicate with all the nodes that are above of them and below of them, as we can see in the following representation. Additionally, in the simulation setup, we perform 5,000 packets, where each packet is transmitted every 15 seconds. And we create a slot frame of 357 time slots in cases of single path transmission, common ancestor algorithm, and Odyssey algorithm, and a slot frame length of 345 time slot for the end disjoint algorithm. By last, the two we perform two scenarios, one scenario with 50% link quality and one scenario with 70% link quality. So in the case of the 50% link quality, we can observe 4 cases of study. In the ones that are in white, this one consists in the normal behavior of Ripple with single path. Then the ones that are in orange are going to consist to the end disjoint implementation with 3 replicas and with an advanced strategy. Then we have the green use case, where we are going to perform the strict median and soft common ancestor methods. And finally, the ones in blue is going to be specifically for Odyssey. So the first thing that we can observe here is that to perform a single path transmission, we require a specific amount of replicas above of 3 retransmissions, no replicas, retransmissions, in order to improve the transmission reliability. So in this case, with 50% link quality, with a number of 7 retransmissions, we are going to have 92.38% of packet delivery rate, or PDR. Then in the end disjoint case of uses, we have the same behavior, where as more retransmissions we have, better is going to be the PDR, the transmission reliability, where with 7 retransmissions we perform 99.96 in PDR. By last, for the strict, medium, and soft CA, we can observe that also we have a good performance with all of them above of 95%, using specifically only one retransmission. And as we were expected, given though that strict CA have less chances to find an alternative parent than medium and soft CA, this one is going to have less possibilities to transmit a packet with a 96% of PDR. Finally, we have the Odyssey implementation, where with only one retransmission we can perform 99% of packet transmissions or packet delivery rate, PDR. In terms of delay, as I mentioned before, in the slot frame can only perform only one retransmission, leading to the scenarios with more than one retransmission with a huge delay and a huge jitter, as we can observe here. And by last, in terms of power consumption, we can observe too that as more retransmissions are required, more is going to be the power consumption, demonstrating that the retransmissions are the main factor that creates the power consumption. Then we are going to move on to the 75 link quality scenarios with link. We are going to move on to the second scenario with 75 link quality, where in this case we can observe that with 7 retransmissions in single path, we can reach 100% of packet transmissions. Also, we can observe that in end disjoint, we only required only one retransmission to perform above of 95% of PDR. And for the rest, strict CAs, medium CA, soft CA, and Odyssey, we have above of 99% of PDR, as we can observe in this figure. In terms of latency or delay, we can observe too that in single path, more given that we use 7 retransmissions, we are going to have a big delay, but with the difference that in this case, end disjoint is just required one retransmission to perform a good link quality, good transmission reliability. So in that case, we are just not going to have to require so many retransmissions to transmit the packet. And by last, in terms of energy consumption, we can observe that end disjoint, in this case, perform much better than the strict, medium, and soft CA plus the Odyssey, given that it just required only one retransmission. And additionally, we can observe that the replication of data packets do not consume as much energy as the ones that it's performed by strict, medium, soft, and CA and Odyssey. So what we can conclude of this work? Well, during this presentation, we learned that in order to introduce the low power and lossy networks inside of the industry, we require transmission reliability and bounded latency. To do so, we use the Ripple routing protocol to produce routes for the packet perform the transmission to perform the reliability of packet transmission. But however, Ripple performs in single path routing, single path transmission. This behavior is not good enough to perform in the quality of service requirements of the industry. So in response to that, we established 2 types of multipath routing patterns to improve the transmission reliability in Ripple. The first one, disjoint, which create a parallel path from the source node to the target node, is able to support 2 types of pareo functions, which are the the replication and elimination function and the retransmission option. And also we will able to create an algorithm denominated n-disjoint, which allowed Ripple to work with the disjoint pattern in order to improve the transmission reliability. And the performance that we get here is that in in scenarios with low link quality, n-disjoint, the algorithm n-disjoint depends specifically in the retransmissions in order to perform its transmission reliability. But in scenarios with good link quality, in this case 70% link quality, it performs much better than the other braided algorithms, CA and Odyssey. Then we have the braided, we also demonstrate the braided pattern, which is able to support the following Pareo functions: replication and elimination, overhearing, and retransmission. And we were able to create two types of multipath algorithms denominated common ancestor and on-demand selection. And what we learn about these algorithms is that both of them, they ensure reliability even though if they are in bad link conditions or good link conditions, and also they ensure bounded latency, given that they just required one retransmission to perform their transmissions. However, as we can observe too, given that the replication that have uncontrolled replication that have CA, we have to in this case we have to perform Odyssey to improve the specific number of relay nodes used in this transmission. And for the perspective, what we're missing in this investigation is that we require a dynamic scheduler that can be modified itself to satisfy the routing changes of Ripple to maintain unbounded latency. Also, it will be, as I mentioned before, the Pareo functions are independently, and in this case, we just tested with Ripple that is a proactive routing protocol. So it will be interesting to test it with another reactive protocols to see their performance. And most importantly, in this case, we use a controlled scenario with a specific type of topology. But given the conditions and the objective of Ripple, it will be more interesting to perform some experimentations where we can produce random topologies scenarios to see how these algorithms and functions improve. And by last, we should also try the multipath algorithms that they were provided in this investigation in other type of routing protocols in order to demonstrate their behaviors in different routing protocols scenarios. So ending with my presentation, these ones are the following publications were the publications that I did during my PhD time, where in 3 of them I am the main author, and 2 of them I am a co-author, and we also have a journal publication that is that I didn't mention here just because it's still in corrections. And here I finish my presentation. I want to thank you all for your attention, and thank you very much for listening to me and my presentation. Thank you.
Thanks to you, Thomas, and thanks for the presentation. So I'll hand over to Nathalie first, Nathalie Mitton, who reviewed your manuscript.
Yes. Hello, can you hear me?
Yes.
Yes, so first I would like to thank you for this presentation and also for the manuscript. I have a few questions, as you can imagine. First is more, I would like just to come back on different figures that you just show and others that are in the manuscript, because I'm not sure to have understood everything. So I have a few questions on this, which are more relative to curiosity. So first, it was figure in the manuscript, it was number 4.5. So actually, it was a number of relay nodes per transmission. Do you see what figure I am? Do you have it? Do you have your manuscript here?
Yeah. I'm going to the manuscript 52. Right now.
Okay. So in the y-axis, you have the number of traverse nodes. So, so I guess it's the number of relay nodes. And what we see is that the number of nodes increase with the number of retransmission. And I was wondering why. And also it increases for a single number of retransmission. It increases with the number of pass. So I think there is a misunderstanding from myself and what you represent exactly, or there is something I missed. So I just wanted to check with you.
What is the number of the figure again? Sorry.
4.5. No
4.5.
It's page 52.
Yes. Average relay nodes per transmission using n disjoint.
Yes.
So
just to be sure, in the y-axis, what you represent in the number of nodes on the pass, right? So if you have one pass and that you have to just to retransmit, so it's just the number of RTX which will increase, why do you have more nodes to traverse? Since it's the same pass. You see what I mean?
Not really, sorry.
Thomas, just if I may, could you please keep sharing your slides so that everyone can see what?
The figure that we are talking about, yes. So it should be this figure, right?
Yes. What I didn't understand is, if I understood well, what you represent in y-axis is the number of nodes that the packet goes through from the source to the destination. And what we see is that the number of relays increase with the number of retransmission. But if there is one pass, the pass is the same. It's just that each relay will retransmit, but the number of relays should be the same. So this is why I didn't understand this.
All right. So this is because the link quality, in fact. The reason that as more relay nodes are used is because the packet could go farther than the point that it reached. So this means that if I have more retransmissions, I have more chances to perform more hops, meaning that more nodes are going to be used.
Because you take also pass who fails. You don't take only successful pass, right?
So in this figure, most likely it represents the average number of nodes and of relay nodes from the source node to the target node used during a specific transmission. Well, in this case, we take the average of the 5,000 packets that we use.
Of course.
So in this case, in fact, we can observe the figure with 50% link quality, and it should be also the figure with 75% link quality. In this case, given that we have a poor link quality, the packet have more difficulties to reach more hops. So as more retransmissions I use, more chances have this packet to go
and
through.
You go further. Okay.
Yes.
So it's just because you don't take in your statistics, you don't take only successful pass, you take all tries.
Exactly, it's the
Okay,
average.
so I missed that point. Okay, so it's much clearer and logical now. Okay, sorry about this. Okay, and there was another figure I didn't get. But I think the answer will be the same for my other question. Okay, and also what was not clear for me was because everything you were talking about, your figures with latency, you also talk about the jitter.
Yes.
But, okay. I didn't see where the jitter was represented on the fig.
Okay.
Is it the small square we have inside the other one or something like this? Yeah.
So the jitter is represented in the graphic as a standard deviation.
Yes, yes, of course. Fig 3.8, for example. Yes.
Sorry, which one?
3.8. For instance, just one over 3.8.
Okay. Delay and jitter.
Yeah, for instance, where is the jitter? Is the jitter the small square inside the other one?
The jitter will be the the string line that is above the square of the delay.
Okay. Okay. So I think you should better explain it in the manuscript when you describe the figs, because it's not so straightforward. Actually, it was not for me. Maybe it's only me, but okay. Thank you. Okay, so my other question were less curiosity, but more investigation, if I can say. Did you try to evaluate the ratio between the success, how can I say? Because you show that, okay, when you send more message, of course, you have a better reliability, and you, but this costs you more energy. So that's normal. But did you try to evaluate the ratio between both to check which one of the different solutions that you show us provide more or less the best compromise, the best trade-off between these two metrics?
Okay, that I can show it in one of the slides that I present. In fact, I'm just going to share the slides again. Okay, so first of all, I'm going to move to the PDR in scenarios with 50% link quality. So as we can observe here, and this join requires several numbers of retransmissions, in fact, to perform a good transmission reliability. In this case, we can observe that we can reach 99.96 with 7 retransmissions. But if we move on to the cases with 70% link quality, with 1 retransmission of this join, we can perform 96.44 in PDR for the transmission and reliability. That is also pretty good, actually. So, in what thing I want to reach here? Well, as we can observe here is that, just to say it, that all the other algorithms, strict CA, medium CA, soft CA, and Odyssey that perform the braided pattern, they are close by to 96 and above. But in terms of energy consumption, if we end this join, given that it doesn't perform the braided justification and just perform the single path behavior, and also replicate. I mean, it doesn't require to do a braided pattern to perform its behavior. Less transmissions attempts are going to be performed. So in this case, as we can observe for the end disjoint, the power consumption is way lower than if we compare that with the strict CA, medium CA, soft CA, and Odyssey. But if we move on to the 50%, this is way different, because as more retransmissions are required, more is going to be the power consumption. So there's two things here. First of all, the transmissions that they were performed with the braided patterns, meaning strict, medium, soft, and Odyssey, they perform similar behaviors in terms of PDR and power consumptions in both 50 and 75 link qualities. But for end disjoint, its performance of 50% is worse than the strict, medium, soft, and Odyssey, but it's better than these four algorithms in link qualities that are much better. So in response to that, well, we didn't, in fact, did a full analysis about that in the thesis, but the main idea about about your question is that depends of the characteristics of the network. So in this case, I will say that the performance for end disjoint algorithm with multipath will perform much better in qualities that they are much that they have better probability. But if I want to keep a stable transmission reliability, I will perform strict, medium, soft, even though it's just to make sure that even though what type of link quality I have, I make sure that I'm going to keep the same transmission reliability. So that is and that's where the trade-off about the about transmission and transmission reliability by multipath and the power consumption. And again, it's really important too that we have to understand that as the power consumption goes specifically where the if I use more retransmissions during the transmission. In fact, the retransmissions are the ones that spend more energy, as we can observe in the following in the figures that I show here.
Mm-hmm.
I don't know if it was clear.
Yes. I got your point. Okay. You evaluate your approaches with mainly on grid topologies. And I was wondering whether you test over other topologies, random or with big holes in your grid, because we can have some failures from nodes, or we can have some mobile nodes, so that can make the topology change. Did you try other topologies?
No, not really. I didn't. We didn't try other topologies in order to be fair with the rest of topologies. In fact, this is one of the perspectives that, and they are in the thesis, that we have to try different topologies, given that the one that we have, it gives us results, but it doesn't give us the full picture of how is the performance of the several algorithms.
Mm-hmm. Because I was wondering, as you are using only a regular topology, which is very regular actually, if you had analyzed where you have some duplicated branches that appear and why, because since your topology is completely regular, it can be done, it can be replicated, yes. Just based on the traffic, maybe, or not, because as the topology is the same, there is no way that at some point you decide to split at other nodes. So did you analyze why you have some splitting sometimes?
What do you mean with splitting?
When you need to, okay, you start with your medium CA, and in the best case, you go only with strict CA because you will have less spreading in the pass.
Okay.
But you allow you to have more freedom to go to, I don't remember. Oh, but okay, what will make the algorithm, as your topology completely regular, what will cause the fact that you will change from a strict CA to medium to another one?
All right. So first of all, this type of this topology, in fact, is a topology that we created with a Kuya simulator, and in fact, we are using the methodology that Ripple give us, and also the ETX metrics. So that means that if we are, even though using a scenario with 70% link quality, the path selection goes through Ripple, meaning that we have to go specifically of the ranks given by the objective function of the routing algorithm. So let's say that we miss one control packet, in this case a really important one, DIO packet. Then these nodes, they are not going to be updated with the related information. And also, given that we are using ETX, if a packet get lost, means that the rank that we are going to that node will have can increase, making some nodes in that specific layers not able to be selected as parents, in fact. And during our simulations, we observed that in many cases, a node was not able to find an alternative parent just because of those problems.
Okay. And I think what will be my last question is, so Ripple, as I think that this is the biggest advantage of Ripple over its other routing protocols, is that it can allow multi-instance. And so different QoS level or everything. Why, or maybe not why, but okay. Did you at any time think to use this multi-instance?
No. In this work, we focus specifically in the methodologies of create multipass. So we didn't.
Yes, but maybe there was a way to use this characteristic of creating multi-instance to create multipass.
It's a possible way. Yes. In fact, that can be a trade-off of
on the objective function, on the different, yes.
Exactly. But no, we didn't try it to experiment with this use case, with that use case.
Okay. Okay, thank you. So thank you again for everything. And Mr. President, I leave you the floor. Thank you.
Thank you. So I will hand over to myself now, since I reviewed the manuscript. So I have some questions as well. But first, I would like to congratulate you about your presentation, which was very clear and comprehensive to me. And also congratulate you for your manuscript, which was of high quality, and we were able to understand your motivation and also your contributions. So it was overall very comprehensive and interesting to follow your methodology throughout your PhD period. So thanks again. I have first some questions about your core contributions, and before going there, I would like to mention some mechanism that you have in your replication and elimination function.
Okay.
You mentioned the history cache, a cache about the unique ID history that you have.
Yes.
I'm not sure you mentioned it during the presentation, but I saw this in the manuscript. And you especially mentioned that the size of this cache could be set based on the maximum data traffic possible and also the maximum end-to-end delay. So I was simply wondering if this cache was set once for all during your simulations, or did you try to adapt this during your evaluations?
No, it just goes through the same parameters and during all the simulations. We didn't adapt it.
Okay. And do you think that could have an interesting impact or something valuable for improvement? Okay.
To be honest, I don't know.
Okay. Yeah, I was wondering the same. To what extent does it play a role, minor or major, in the end results? So
yeah.
That was a detail. Then I will move to the strategies that you have. So the advanced strategy against the basic one. So as expected, you get better results with the advanced strategy. But so it's quite expected. But still, I was wondering if we couldn't think of some topologies or configurations in which it wouldn't be the case. So in this topology, indeed, you have the relay nodes that are able to also perform multipaths. So we get some advantages. But could we think of some other topologies in which it will not be the case?
For you meaning for the path merging?
Yes, exactly.
Okay, so the main idea of the basic strategy and the advanced strategy, in fact, is just to allow the nodes to merge. But if it's not the case, Ripple can behave as normal as the disjoint pattern, depending of the topology. So even though that we are using an advanced or a basic strategy, if it, in fact, I can show it in the example here. Even though that it's possible to have a parse merging, we also have cases that we are not going to have that, and that's also depending of the link quality or depending of the topology. This two type of strategies, in fact, is just to allow perform Ripple how it is, and not giving extra rules to Ripple to obligate it to work anytime to perform a disjoint pattern. Because as I said before, in fact, in the presentation, making Ripple behave all the time to disjoin is not the objective, in fact, of Ripple. Ripple just look at the best path by the objecting function. So given more implementations to make Ripple to behave as always a strict disjoint pattern, just brings complexity to the implementation. So if we have a topology that, let's say, we don't have a connection to do the merge path, it also will work, because in this case Ripple is going to be the actor of selecting those paths. So if those nodes, they only have one unique chance to select one parent that is going to be the forwarded parent to create the disjoint parent and the disjoint path. Well, this algorithm will work too in that case.
Okay, and to continue on this, I was thinking that maybe when you get closer and closer to the sink, this disjoint strategy is not the best anymore. I mean, when you get closer to the sink, you have less and less disjoint paths, no? And so I guess less and less would be.
It is true. It is true that well, depends. If we think that the DODAC behave as a, I know that is not correct, but it can is we think that a DODAC is a tree, then can be the cases. But in this case, Ripple and a DODAC is not that. It can take many ways to reach to that specific destination. So again, that in fact depends of the conditions of the topology. In this case that we can observe in this example, yeah, we are going to have more chances that to have a path merging. But one important thing too is that to contrast the path merging with one unique single path, this strategy also requires retransmissions. So again, we have to play we have to balance how many retransmissions we require with how many paths we can create. So if I cannot, if I know in that many paths are going to merge specifically at the sync node, then for sure I'm not going to have so many replicas to transmit, because a lot of them, they are going to be merged as we observe in the basic strategy. So to contrast that, if we want to improve the reliability, the only way to do that will be with more retransmissions.
Okay, and it will move to, then we can move to, sorry, to the common ancestor. And because when you get closer to the SIG, maybe it has an interest, because the common ancestor requires more knowledge than the end disjoint. Since you,
yeah, well,
I didn't see how it was managed concretely. Like you exchange the parent sets, and or only the preferred parent and alternative parent is enough for the common ancestor algorithm.
So the thing with the common ancestor is that it focuses to a different type of strategy. In fact, the to recreate a common ancestor selection, this one required extra information that we are sending in the control packets, in the DIO packets, in fact, where we are sending the parents information of the selected parents addresses inside of the DIO, so this DIO can be broadcasted around the neighborhood of that specific node. So in this way, we can make the word is we can think in the future about no, the word is guessing. We can guess most likely which is the preferent parent and alternative parent of the specific preferent parent that we are targeting with, and that's how we can create an alternative parent. But also this implementation has problems given that it requires the DIO packet. So if this DIO packet get lost, we are not going to have the update data that we should require to select a proper alternative parent. And that is one of the main issues, in fact, of the common ancestor selection. In the case of the disjoint pattern, this is not the case. In fact, it doesn't require of the DIO packet to obtain the information of the other neighbors. And disjoint just go specifically with the objective function that we have. So in this case, we just move on with the default objective function of Ripple, in fact.
Yeah, that's why I was wondering about the complexity of common ancestor. But because if I remember well, you used 5 layers for your performance evaluation of common ancestor, and with 6 nodes per layer. So did you try to increase those numbers first, and second, you used only one source at a time? And what if we have more data sources in the network?
So during my PhD, in fact, I keep the same topology with the same amount of nodes, the same amount of hops, and the amount of layers per node. So all the results, in fact, that are in the thesis are exactly the same ones that you can observe in the several publications that I did. We didn't try it with bigger topologies, but we have been tested the number of relay nodes used. That doesn't go too much about what we are talking about in this question, but what I want to reach here is that um, I guess that with a bigger topology, a bigger topology will not change too much about the results, but worse link quality will change way much more the behavior of the common ancestor strategy, given that more control packets are going to get lost.
Perfect transition. That's my next question. I was regarding this mesh topology that you used. So you used the link quality homogeneous over the set of nodes, the set of links. Sorry. So I'm correct, I guess. You presented two sets of results, one with 50% of link quality and one with 75. And I was wondering if you tried to have topologies with random link qualities on links. Why this choice of homogeneous link quality over the set of links?
Well, we did it too with random topologies, but
not random topologies.
Sorry, not random topologies, random link qualities in the topology. And well, in fact, we observe that if we create a set of link qualities between the 25% to the 75%, we have this 50%, an average of 50%. But we observed too that the behavior of that random topology was a bit worse than the just static 50%. So to be honest, if I want to check a better result in scenarios with random topologies, in random link quality, sorry, I will focus specifically in real environments, because in simulated environments, I don't think that we can recreate a very good data, in fact, just because I feel that this is just probabilistic. So if we move on to random 25 to 75, we are going to have close enough values as the just fixed 50%.
Okay. And because my question about this was also because the Ripple parent selection plays a role in there, and so these link qualities, if you have heterogeneous link qualities, so if tomorrow you mentioned this in your perspective, so if tomorrow you plan to deploy your protocols on real environments or real experimentation hardware topologies, what would be the main adversaries to your to your solutions, in your opinion? Is it the Ripple parent selection, or is it the, well, we'll speak right after about the underlying TSH schedule, but
well, the main bottleneck of all this implementation is, in fact, is that not find any alternative parent at all, and staying just with single path selection. That's, in fact, is the main bottleneck that have all these implementations, and that can be happen if, in fact, this can happen several times with the CA implementations and the end disjoint implementations. Given that, as I mentioned before, all the selections depends of the ranks in Ripple. So if there is not any available parent to select as an alternative parent, then I don't have any chances to improve the transmission reliability, and then I have to perform just single path transmission.
Maybe one last one or two last questions. You to broaden the scope here. You mentioned the quality of service parameters that would be required by your target industry application. It was so there are many different application scenarios.
Yes.
And so each will come with its own QoS parameters, and that would need to be translated into something in your solutions. So I was wondering what this something would be for you, or the most difficult thing to translate. If we come with this is the latency I want, this is the end-to-end reliability I want to obtain. So how can you configure your protocols and solutions?
So in response to that question, in fact, I will say that in order to improve the quality of service in the low power and lossy networks, these were first target the reliability, and also we wanted to target the bounded latency. The reliability depends, and that was what we discussed before. Depends most likely about the neighborhood. If I don't have any nodes to replicate the data, I have to just go with the retransmissions in order to improve the reliability. In terms of the bounded latency, and I think that this is the most challenging thing that we have in this implementation, is that the scheduling that we use is a fixed scheduling, meaning that if one of the nodes move to another distance or does not correspond inside of the scheduling, then we are going to have a dead node. And the main problem with the scheduling is that it have to go along with the Ripple routing protocol, and we know that Ripple, in fact, doesn't require to the other layers to work with. It's a really independent routing protocol. It doesn't require of the MAC layer or any layers, network layers above. So the problem here is to create a communication, is to create adaptable scheduling that can behave at the same time that Ripple requires to change one of their parents, in fact. And I think that that is one of the biggest challenges right now that and this work is missing to improve the quality of service in the industry.
Yes, I totally agree. I didn't insist on this part because you mentioned it indeed that you have a centralized teach schedule, and it was not the purpose of your research work to get this. And I guess the next members of this committee will have some questions about this. So I will not take more time. Thank you for your question, for your responses. Sorry, and now I will hand over to your first examiner. I will use the alphabetic order. So Diego Diovne can start. Thanks a lot, Tomás.
Okay.
Thank you.
Thank you a lot for your presentation. It was really very, very nice and clear, and also for the work you did on the thesis report. Okay, I found a very interesting insight on what you have done, and the results also were pretty clear too. Well, first I would like to go through a little bit on some interesting topics you have been answering questions about, and the first should be the idea again of topology, the third one that says so, but talking about energy and the remaining energy on the whole network, and the idea of thinking about each of the nodes which can fail after the energy depletion. Okay, if you have no more energy available about the node, so it turns off, or it gets on power saving mode or whatever. So these road changes, or how do you think RPL manages them correctly, and then you adapt after the parent selection, or you are getting some other path alternatives after this happens? What happens if a node fails in between because of this?
Okay, so if the node fails, I mean, if not fails, dying, given that it doesn't have any more energy, in fact, we just go through the repair method that Ripple provides. So, in fact, this is a really interesting thing, just because also bring us delay, given that during the repair timing, we have the algorithm have to find a different path to keep forward the packet, right? So uh, the algorithms that we implement here, in fact, they don't care if the nodes died or not. If the DIO packet that was sent by Ripple show that one of the nodes die, because in fact the DIO packet update the information that is in the network, then the neighbor nodes are going to be able to find a different preferent parent. And if the case that we find a different preferent parent, then we are going to choose also a new alternative parent. So the important thing here is that what we want to keep during the multipath parent strategies is that when the preferent parent dies, it doesn't matter if the alternative parent is valid. We are just going to change the alternative parent in order to make the alternative parent related to the new preferent parent that is going to be selected. And if it is that the case, normally the actual alternative parent that was selected move on to as a preferent parent, given the rank values of Ripple. So
Okay.
that's how performs these algorithms, in fact, if it is that the case of when nodes dies.
Okay, so the thing is, the idea that the node dies, I mean that some way somebody has spent more energy than the other ones. The whole network is not dying all complete at the same time, but there are some up and down. So I think that from what you have shown, from the topology you have shown already on your presentation in your thesis, the grid, okay, helps you on keeping all the consumption mostly uniform. But on other topologies, this will not be the case, maybe. So the energy consumption dispersion, so be the nodes are keeping more energy on one side and nodes that are being depleted faster on the other side. Okay, that will that will have a certain consequence. That the thing is, several nodes will die in the middle on some places, or mostly close to the to the destination. So to the Dodak route. So my point of view there is that what do you think that this dispersion will happen? Okay.
Well,
Have you ever
the
tried some other
yeah,
topology
no,
that
I
this?
understand the question. In fact, the behavior that you are explaining about is the load balancing uh, behavior. The thing is that in this work we didn't focus specifically in the load balancing. What we focused on was the transmission reliability.
Mm.
So in terms of energy consumption, we know that that many nodes, they can be oversaturated if we have many stores that are transmitting, because at the end of the days, these implementations are replicating the traffic along the DODAC. So yeah, it's a big issue, but that is, and in fact, that is one of the main reasons that we just implement one source node in the DODAC. But yeah, well, there are many implementations, in fact, in the load balancing, and one of the most common one is to send a metric showing the lifetime and the waste of the lifetime that still have the node. So in this case, we just place with ETX, which allow us to follow the best path to do the transmission. But this these methods also can rely on other metrics. So in this case, it will be interesting to merge, let's say, the ETX, or just remove the ETX and just use the metric of the amount of energy that the other neighbors use in order to perform the packet replication to those nodes that have more energy. But again, this doesn't go with the methodologies that go with the algorithms, but it goes specifically in the objecting function that have ripple.
Okay. So just answer the following question: what would happen if I use several sources? And that also goes through the idea of scalability. What happens if you have 10, 100 or 1,000 nodes? What would happen in this kind of situation if it was sustainable, this whole solution? So going through to other question or other idea, talking about the talking about the scenarios that this may be applicable, maybe I'm thinking about two ideas I got during your presentation. The first one should be the an underground mining, for example. Okay, with the tunnels, you have to transmit information through the channels themselves. And the other one will be the poles in a city where you have to transmit information about whatever you're measuring, the power consumption, the state of the lights, whatever. So do you think that this is applicable directly to those? Okay, do you think that you can map this idea to those kind of applications?
Well, taking the example first of the underground mining, I think that the goal here and there is to improve the reliability to transmit a packet, given that the environment of being underground doesn't allow very well the wireless transmission.
Mhm.
So in this case, I will say that multipath will these strategies, in fact, to provide multipath in Ripple will be a good example to as a use case. In terms of cities and stuff like that, we also require reliability. But given that the cities they have open environments where the wireless can work more fluently than in underground, well, in those cases, I will say that uh, we uh, we require scenarios that we save more energy, given that we don't want to replicate this packet and make all the devices suppress all their energy. So just to clarify the answer that that I'm saying, I will say that in the first scenario, I will go through a best effort link quality scenario, while in cities scenarios, I will go to more sustainable energy scenarios, where in fact I will use Odyssey, just because it uses the fewest amount of nodes to replicate the packet with big PDR transmissions.
Okay, and finally about the perspectives you mentioned in last part. I don't remember if I catch every one of them, but maybe you mentioned about the experimental work on experimental platforms, or I missed those.
In the perspective, well, in the perspective, I said that we required a more dynamic scheduler first for Ripple for the behavior. I also said that we required use pareo functions, and not the ones that they provide packet replication, retransmissions, and overhearing to other type of routing protocols. Given that we just tested with Ripple, so a reactive routing protocol will be good too, just because is the opposite as Ripple. Given that Ripple is a proactive routing protocol, I also said that we just test the algorithms in a fixed scenario, by doing simulations. But being realistic in a real scenario, we don't have these fixed scenarios, and that I think that will be the next step also for these algorithms to see really how they can improve in random scenarios. And by last, I said also that the multipath algorithms as the same as Pareo, but we have to be careful. These two concepts are different. The Pareos are the functions that help the packet to go through, and the algorithms are the path that we are taking. Use it in different routing algorithms as other reactive or proactive algorithms.
Yeah. And on that side, okay, so you think you are going through or trying to test this apart from simulation to go to experimental such as fit IoT platforms and so on, or you think it's the complexity now, or something you are missing something there in the between, or just the amount of work will be?
Well, by now, what we are missing, and that's I mentioned before, is the scheduling for real scenarios. But that is something that I didn't focus, in fact, in this PhD, so I cannot provide so much information about the scheduling. But with the experimentations that we have, we already gain and simulated scenarios really good PDRs for ensuring the transmission, the quality of service in the industry for transmission. So I think that the next step is to demonstrate how these multipath algorithms can go through real environments and see how they are behaved. But before of that, I think that is more important to find out a type of topology that, not topology, scheduling that can be adapted to the changes path and movement that have these nodes using Ripple.
Okay, thank you. Okay,
thank you.
Thank you, Diego. I will pass the word to Bruno Coitin from Université de Mons. Thank you.
Okay, hello. Thank you for your presentation and your report.
Thank you.
I would like to start with the clarification about the manuscript. I have two questions about two sets of figures. The first one is in chapter 5 on page 65. It's about the number of copies of packets. So chapter 5.
Chapter 5.
65. Figure 5.68.
4.
Okay, yeah, here you are.
Okay.
Okay. I was wondering what is the exact definition of your of the number of copies per packet? Does it also include retransmissions?
Okay. So not really. In fact, average number. Okay. So at the time that I'm doing a transmission, in fact, each time that this packet is going through several nodes, is going to replicate this information, right? So wait, the thing is, I have to analyze the figure again because
you could start with the first column. If you consider for the 50% link quality, the column with one retransmission, so RTX1, you seem to have 6 copies per packet.
So yes, it's a number of is per retransmission. In fact, is the average with retransmissions. So how many times the packet was replicated, in fact, with retransmissions? Yes, sorry.
Okay, but here you have a 6-hop path. So it means if I have 6 copies, that means that on every hop, the packet was each time successful. Because if I have 6 copies along a 6 hop path, it means that there was no failure. So it was kind of surprising me, but I certainly missed something.
You are talking about the scenario single path?
Yeah, single path, a single retransmission, so RTX1.
RTX1.
First column.
All right. Well, if it provides one retransmission, means that is one transmission plus one retransmission, right?
Yes.
So each time that the packet performs a hop, it requires one transmission and one retransmission, and we are talking about 6 hops.
Yeah.
So 5.8 means that in average, the packet have been transmitted and retransmitted one specific packet. I mean, we are talking about the average of those packets 5.8 times. So it doesn't mean, in fact, that it reached all the time to the destination. In fact, at the time that we are doing, and that will the case if we don't have any retransmissions at all. If we have one retransmission, we are duplicating the chances. That's why we have this value, in fact.
Okay, so if we had 100% link quality, then the number of copies in this scenario would be 0, right?
No,
if I understand
it will be 5. Because we are counting each time the packet was forward by using normal transmission and retransmission. So in this case, let's say that if we have 100%, then we are going to have the same amount of hops used for the transmission. So in this case, I think that we have to pass through 5 nodes. So the value have to be exactly 5. The copies here is that we count how many times that copy have been transmitted from the source. So 1, 2, depending if it is a transmission. Then we count the second hop, and so on until we reach to that number. So in this case, I will set that in normal case, if we use all the retransmissions, we get around 3 hops. Because it's 1, 2 from the source, 1, 2 from the first hop, 1, 2 from the second hop.
Okay, I guess you should probably clarify your metric in the text, because it's not obvious to understand that, and it leads to questions about the figure. And I have a question about another figure, which is about energy consumption. So
okay.
It's in the same chapter, and it's next page.
Mm-hmm.
So here it was also not clear to me what you mean by power consumption. So on the y-axis, in the text you say, let me check. It's the total average energy used by each simulation.
Yes.
So it means you provide the cumulated power, because you express that in milliwatts here. Is that over all nodes, over the whole duration of the simulation?
Is over the whole duration of the simulation, and in fact for all the nodes. We take all the nodes independently for their and we measure their power consumption from the starting of, not starting from the simulation, in fact, from when the DODAC was created until the simulations was finished.
Okay. Because, well, if I look at the worst scenario, it is single pass RTX7.
Mm-hmm.
I see, well, 0.30 milliwatts, 0.13 milliwatts, right? So 130 microwatts.
Yes.
That seems very low.
It is low. It is low, and this is because, well, it is low, but we have to understand too that in the scheduling that we are using, there are many cases that we are not using the radio.
Yeah.
It can be higher if we use more, if we keep the radio on more often, in fact. But in this scenario, we are taking the radio on when we have been transmitting the packet, and also when we are not transmitting the packet, meaning that the scheduler obligate the node to turn on, even though that doesn't require to transmit or receive the packet.
Okay. Perhaps it would help to provide some kind of baseline where you document what is the consumption of a single node in its different radio states.
Okay.
So that we can compare with the figures you provide in the report.
Okay.
Then I have a question about the technique you explain in chapter 3, overhearing.
Mm-hmm.
In the text, you suggest two solutions to control overhearing. So you mentioned that the first solution is to store the alternate parent in the packets, so that
Yes.
only this parent will process the
Mm-hmm.
packet. Okay, and this is a solution you have used in the.
Yes, in fact, we did it at the time that the packet is going to be sent. In fact, we use the hop by hop option header with the preferent parent and alternative parent addresses. So at the time that this packet have been received, is received by those relay nodes, then if one of the relay nodes do not supposed to receive that packet, we'll drop that packet as a normal transmission.
Yeah. So in fact, it doesn't really limit overhearing. You just filter when the packet is received.
Exactly.
But you discuss another solution. You said, okay, another solution would be to arrange the scheduling in the slot frame to limit overhearing.
Yes.
I guess it's more difficult to do.
No, not really.
Can you comment on that? How would you do that?
So that's the thing. We are using a fixed scheduler. So we know, and well, maybe it was bad understand it, but we are using the both methods. We are sending information of the preferent parent and alternative parent inside of the hop by hop packet header, plus we are setting specific slots for the alternative for the overhearing. And given though that the topology is static and the scheduler is static, we can provide that. And I can show you that in fact, I can show you an example where this is the type of topology in the scheduling that we are using, where in parallel of the retransmission, we specify the nodes that are going to be overhearing, and we are taking all the possible scenarios. So given that also we create a really big slot frame, but the idea of the slot frame is to coverage all the type of scenarios that we can find during one specific transmission, in order to not waste energy just for overhearing, to just keeping the nodes listening all the time.
Mm-hmm. So here in the example you provide, A and B will always listen.
Yes.
When the source sends to either A or B.
Exactly.
But then this would increase the power consumption, right?
It will increase the power consumption, of course, because we are letting the nodes to hear when they should not hear. That is a reason that also I was mentioned that we required a dynamic scheduler that can control those overhearing and hearing slots.
But that is also why I was surprised by the power consumption numbers, because I was, well, they seemed so low.
Yeah.
While there are quite many nodes that are listening in every time slot.
Oh yeah, no, we understand the concern, in fact, but maybe in fact is we know that the power consumption is low, but maybe we just took the information that the simulator of Kuya gave it to us, provide us. Maybe there is something. Maybe there is something that we are missing. We are not sure, but in fact, we used the information that the simulator gave it to us in order to perform that.
Okay. Then I have a question about the traffic. So this has already been mentioned by Antoine before. You used a single source. So, well, it's kind of an ideal case. What would you need to do or to consider if, for example, instead of having just one source at the bottom of your grid topology, you had, let's say, 10 sources or 100 sources, and they all have to share the same topology? So
well,
my idea is that, well, first you would need to change your schedule and change the slot frame. So this would make the latency worse. And perhaps you will, since you have some kind of cross traffic for each flow, you would need to also consider the depth of the queues on each of the relay.
Well,
I've seen the queue mentioned in the previous.
Well, in fact, the problem, the issue about many sources, in fact, go specifically to the scheduler, because the scheduler is the one in charge to do the transmission and reception, right? So if I have many sources that they are transmitted at the same time, then the scheduler is the one, in fact, that have to decide which one is going to transmit first, or which one have to be dropped, or etc., 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 depending of the scheduler that we have. But if we talk about the algorithms that we were using, that they were developed, in fact, in this thesis, I think that with the multiple sources, it still is going to behave all right, given that they just dedicate specific routes to reach to that specific target.
Okay. Then I have perhaps one question about your link quality model. I guess here the probability that a packet fails, it's independent of the other packet transmissions, right? So for each packet, if you have a 50% link quality, you will basically pick it passes or not.
Yes. So yes, it's independently of the link
packet or over another packet that is sent simultaneously. For example. So it's not the most realistic model. So usually you can have kind of bursts of interferences. So interferences that would last for several consecutive milliseconds, for example. And so since in your approach, typically the redundant packet, they will be sent in a very close time, such burst of interferences would affect the original packet and its replications, right?
Yes.
Okay.
Yes.
Can you comment on this?
In fact, well, if I give a honest answer, these were simulated by Kuya nodes, meaning that there is not any simulator interference or stuff like that. In fact, that they can affect in the environment. What we in fact play here is a probabilistic way of success. In fact, if we are if I can explain myself. So if that is the reason that one of the things that we required for the perspective, in fact, is to test these nodes in real environments, or yes, in real environments, because in those real environments we will be able to find other problems inside of the interference, such as noises and stuff like that. So yeah, like the results that we have here is just the results that we get it by a probabilistic method. We cannot provide results of the conditions, the environmental conditions that a wireless transmission can have, given that Kuya, at least in the configuration that we have, doesn't provide us that tools.
Okay. Yeah. So my question was not really a criticism of your model and methodology. It was more, well, now if you realize that in practice, consecutive transmissions could be affected. Perhaps how would you change the way you provide redundancy? For example, you could delay the replicated packet, so that is not affected by the same burst of interference.
Well, let's go through the implementation on the queue, right? So, and again, when the also that goes specifically in the scheduler, when that just because the scheduler is the one that in fact says when the packet is going to be transmitted. So I guess that in fact I cannot give you a sure answer about the question, but I think that the way that to solve this problem is by scheduling this packet in the scheduler, like letting the nodes know when it has to transmit that specific data, and then transmit this and the second traffic, the packets that are in the traffic. But again, I will not say I will not know to say in fact what is the best method. I think that the methodology will be go through the scheduling.
Okay. I have a last question, which is also about the strategy. Here in your work, typically you pick one strategy and you stick to it when you forward a packet from the source to the destination. But I was wondering if it would be interesting to allow a change in strategy along the path. For example, in the topology, it's not the case in the topology you have been using, but in a perhaps more realistic topology, you could have parts of the network where you have a lot of diversity. So you have many neighbors, and from these many neighbors, you have many paths to the sink. But in some part of the topology, perhaps you only have a single parent that is available. So my idea was perhaps when you have many neighbors and many possible parents, then you use replication along different paths. But if you have a single parent, you go back to the retransmission strategy. Did you consider that? Is it
well?
applicable?
Yes, no, merging all the algorithms depending of the scenario that we are ubicated, we didn't consider that. The closest thing that we have there is the CA selection. Given that if I cannot do a strict CA, then I will move to the medium CA, and if I cannot find by medium CA, I will go to sub CA. But if we want to merge all the algorithms and use it in specifically places, in specifically situations, in fact, we have to study first in what type of scenarios these ones are, specifically small scenarios, which which algorithm is better. And in this algorithm, we just go specifically in each one of them, as you said. So I can also I will not know in what specifically a scenario we should use each algorithm. I know that we can use end disjoint in cases that we cannot perform let's say the braided pattern, and also just because if we consider that we have a good link quality in those specific cases, just as we observe that end disjoint perform much better than the braided scenarios. Their energy consumption and transmission reliability perform much better in good link qualities. But I will say then that CA, I will use it in the common ancestor selection. I will use it in the worst scenarios, and the Odyssey, I will use it in the scenarios that I can know that I can optimize the parent selection, and I want to ensure a transmission reliability in those specific points. But we don't in the thesis we don't have this information, in fact.
Okay, thank you.
Thank you
for the discussion.
Thank you, Bruno. So we will now hear Pascal Thubert, who was invited to participate in this committee. And so here you go, Pascal.
Hello, can you hear me okay?
Yes.
Cool. Thank you very much for this very nice presentation and for all the hard work that shows in this PhD. I was thinking, just this morning, I published the first version of RFC 6550 BS 00 on the role mailing list, which basically is the starting point for publishing an update on REPL, which would basically not add necessarily features, but clean up the existing writing and remove functions which are not necessarily useful, and maybe add stuff which has been done ever since. And one of those things which are in the original spec and which are related to the work that you've been doing here is the thing we call path control. And so the path control is a set of bits that you can place in your DAO message, so that when you establish through DAO, you establish a route back to you, a bit like when you're forwarding your packets to several parents. Here we're forwarding DAO messages to several parents so as to establish the traffic back from the root. And what we wanted to do with this path control thing was to ensure that there would be some path diversity back to the device, but not too much. So, and that question is the same as the one that you have when you decide to basically do as many replication as you received copies. So you don't want to increase number of copies in flight in the network. Same thing, the path control was like, you ensure that there will be no more than so many paths back to the device. And my question to you is whether you think that this path control function is something that we should keep the protocol, or as we built this new version of Ripple, this 6550BS, or if we should do something like what you're doing, which would be, okay, we can build as many paths as we like, but we will control how many copies of individual packets will be built. So you see, in one case we control number of routes back to the device. In the other case, we control the number of flying packets, but we don't control the number of routes. So is it something that's useful, or should we get rid of that function?
Okay. Well, I will say that it should be good to control the number of copies that we are transmitting, in fact. But also we required a specific way to control the path, because at the we don't it doesn't what is the reason that we create paths if those paths they don't rely in specific nodes to improve the transmission attempts? I will not say that remove the number of replicas will be a good strategy, because then we are not going to in fact enjoy the benefits of the multipath, because at the time at the end the objective of these implementations is to provide path. So those number of replications can merge in specific points to improve the transmission reliability. So
right, which means that because you're always talking on the way up, right? So you're always talking about traffic going from the device to the root, right? Which means that you have unlimited number of feasible parents. Every guide that you can hear, which has a lower rank than you have, is a feasible parent for your design. And so what you do is you control number of copies in flight.
Yeah.
And
well, sorry.
Yeah, and the problem is Ripple right now for the way back does not work like that.
Yes.
It controls the number of available routes because it wants to control the amount of state that is being installed in the devices, mostly in storing mode, right? And the question on the table is it a good idea to control the number of state, or why don't we install all the possible state back? So the reverse DAG to the device, everything that was available to go up should be available to go down, in which case the control would be what you're doing. And that's really where it ties to your PhD, is if we can manage to keep as much state as we can in the network, then we can fully leverage what you do on the way back as well, because you always mention the way up. So on the way down, we should be able to do the exact same thing. But if the DAO constrains number of feasible parents, then you don't have all the opportunities that you had on the way up. So that's why it ties.
Okay. Well, for the downward transmission, in fact, we never, to be honest, I never focus specifically in that case, because at the time that we are using Ripple, we were using non-storing mode, meaning that at the time that if I want to do a downward transmission, we don't have the enough information, in fact, to do that. So
yes, I'm asking you to think out loud, right? Okay. So the other thing is the way you presented it, the DAGs at the very beginning was a bit confusing to me, because want to be very clear is the very design of Ripple is to be able to do DAGs, right? We always mention DAG, we never mention trees.
Yes.
And when you went from that slide, which has a cycle actually in it, EDAB is a cycle, so that is not a DAG, by the way. Yeah. So maybe you should do BA or whatever. And the next slide, you went all the way to a tree, right? So there is something in the middle, which is a real DAG. So if you can fix that slide, that would be nice.
Okay.
And then yes, the whole point of Ripple is to be able to use the DAG. And the research that you've been correctly doing, and that's very nice, is how to use all these possibilities that Ripple has given you of having a DAG as opposed to a tree, so as to improve the like the maximum latency and try to have a bounded latency and to optimize the energy per packet, basically. So once this DAG is fixed, yes, I think the introduction should better say, okay, Ripple provides the DAG. That's a big thing in Ripple. That's core to the Ripple design to have this DAG. How can we use this DAG to forward the packets and get the best latency and bang for the buck in terms of energy versus delivery ratio? So that would be the way to introduce your work more than the tree, basically, that you draw. Based on that, you mentioned that's just a remark, right? That was not the question yet. So the question is more like, there is a chicken and an egg. And the chicken and an egg is TSCH builds a schedule which basically creates links between nodes so that you can forward packets. And Ripple needs those links kind of, so in which order do things happen, right? I mean, does Ripple create the link? And as you said, Ripple is independent of the lower layer, or which comes first, the links or Ripple, right? So you need to find a way to break that cycle and say which comes first. And kind of, obviously, you need to know which routes you need to build and how much packets go through those routes before you can really establish a schedule, right?
Yes. Well, that was a question or not yet?
Well, if you have something to say about that, then that's okay. Then it's more like triggering your reflections again, right?
All right.
How you see the schedule and the Ripple operation tied to one another. What's the relationship between those two?
I will say that Ripple is the one that indicate where the node have to link. And the TACH is the one that creates the link. So this means that if we have a scheduling that do not provide the link that Ripple is performing to forward a specific packet, then we that link doesn't exist.
Right, there's chicken and egg. That's what I'm saying, right? I mean, Ripple needs the links, but Ripple knows where the links should be. So how do you break that cycle?
Well, that's one of the main issues that we are still thinking about it, and that is mainly because TACH doesn't have any clue to know which node have been selected by Ripple in a let's say in a fasted way. I have some ideas, and these ideas in fact are not in any publications. In fact, I just want one of my ideas is to take advantage of the non-storing mode when I'm sending DAO packets, meaning that the nodes enter to the DODAC, right? So we know that at the time that a node entered to the specific DODAC, this node is going to transmit a DAO packet specifically at the root node. One of my ideas here is that at the time that this DAO packet have passed through the nodes that that is traversing until reach to the DODAC root, update the information that is in the scheduling. But to do that, we require a big enough scheduling, which where we can perform all the possible scenarios, even though that we are not using all the time slots for transmission and reception, just specific slots where we can program which is my parent and when I can transmit it. It's an idea,
so basically, So basically, I mean, I tried to summarize what I just heard because I'm not sure I understood it. But what I understood is, before the traffic starts, there is this DAO, which has the child-to-parent relationship expressed with the transit and target information in the DAO. And based on that, the scheduler should kind of schedule already some time slots between this child and this parent, because the child-to-parent relationship was declared, right? And that's a very good answer. That's actually a very good point.
So the scheduler will be created depending of how is in fact is built my DODA.
Exactly, that's a very good answer. And the subsequent question to that is, okay, but that doesn't tell me what kind of amount of traffic this child-to-parent relationship will create on this hub, and then on the rest of the graph towards the root. And that's completely tied to what you're doing here, because you're actually forwarding the packets over multiple paths, meaning that you're using time slots here and there and here and there, right? And so again, you're pushing, it's more dynamic, you're pushing needs on the TSH schedule to create more slots.
Yes, that is the reason that I said that I required a big enough slot frame, because this is not the full idea. In fact, we are just passing through the first method where I'm inserting the node and I'm ubicated specifically in a certain point of the slot frame where I know that I have a certain level in the rank. The other feature that requires this implementation to work with is to update that information, and that can be performed by other control packet that can provide ripple, in fact.
Can you, I mean, I did not get this one. What control packet?
So what I mentioned before is that having by using the DAO packet, we can specify in what level in the scheduler the packet is going to be, right?
What you mean by level is depth in the graph or something.
Okay, so let's say that my parent node have a specific rank, and that rank value will tell me, okay, you should be between this part and this part in the scheduling.
Oh, because you're progressing the packet from the left to the right of the schedule. But that's how you're seeing it.
Exactly.
Okay. Yeah. Okay. So basically, you need to have, as you create children down the diag, you need to create time slots all the way from the left to the right somewhere.
Exactly. And that is the reason that I need a big enough slot frame.
But the problem there is, since you will dynamically adapt the path that this packet will be replicated through, then it's not just one time slot, it's multiple, which will represent the progress of this packet across the possible progress of this packet, right? So you see that at some point you can't really book time slots for each transmission. That's only for deterministic flows. For more normal flows, you realize that you have to have some elasticity here. You need to have some sharing of time slots, and you need to have to allow collision, because you can't just reserve a resource that may or may not be used. At some point, having a very large number of time slots will create a lot of latency across your network.
Exactly. Yeah. No, I understand that as bigger is the slot frame, bigger is going to be the latency. But also, if we don't have a smart slot frame, also we will require more slot frames to transmit a packet, and also that can provide a lot of delay and a lot of jitter. So we have to play off in the trade-off. What we want more, bigger delay or bigger jitter?
Yeah, that's a very good. I mean, that's exactly the sort of thing a researcher needs to come with, right? So it tells the people really what the challenge is. And as you point out, there is a challenge here between overall latency and acceptable jitter. That's a very good point that you're making. The other point that you may keep in mind is 6TiSCH has produced the 6-step protocol, which enables to dynamically adapt the number of cells. And we don't really say this cell is for this packet for this flow, right? We say just this link between two hubs and the average number of packets that circulate there, and try to adapt number of time slots to the number of packets that circulate between those two hubs, and dynamically adapt. And that's probably the best response we have for your crowd. Not the overall schedule, which is really for deterministic flows, which are very well known in advance. But for things which are more stochastic, and since you reroute packets and send copies left and right, it becomes stochastic. The fixed schedule, I guess, becomes a very bad answer. And a lot more dynamic cells between each peer, and adapting, the size of the link, the number of time slots between each peer, dynamically based on the usage, seems to be a better response.
Okay.
So, and that's pretty much it. I really loved your presentation, so thank you so much for it.
Thank you very much.
This is a geodag, but that's really a tree. and
Well,
okay, thank you so much, Tomás.
Thank you very much.
Good presentation.
Thank you.
Thank you. So we now hand over to the advisors. So I can see only Georgios. Georgios, maybe you can start. Nicolas must be in the room, but I let you agree on who should start. But the word is now to the advisors.
I don't really have questions from my side. I just want to say thank you to Tomás for these 3 years working hard.
Thank you.
I hope you enjoyed these 3 years being with us.
No.
It was really nice. I mean, it's true that the subject is really large. We can see this. We can not solve, but we can tackle this problem from many different point of view, like the one that Pascal mentioned with the TAO, the one that Natalie said with multiple instances. I mean, there are many different ways to come up with this, to the same objective. And I mean, I was a witness of very hard work that Tomás had to go through, because Contiki is not as simple as sound. I mean, to work over, there are many files, a large size of code. I mean, I went through as well during my PhD, so I know that some months Tomás had to work too much to get one single figure, one result, to understand the behavior. And sometimes Zilber wasn't working properly, the sketch wasn't working properly, so it was not an easy task to do something over work. So I can say that Tomás is a hard worker, and he managed well to anticipate such tasks. And of course, regarding the research part, I mean, it was quite interesting having these discussions, and he was coming with multiple different ideas, especially with these 3 different CA algorithms, and eventually at the end, the ODC. It's a work that manages to somehow to present a trade-off between these 3 CAs. It was quite nice from the research point of view, and was really 100% his work and his idea, his proposal. So, just congratulations, Tomás. It was really nice to have you here.
Thank you.
All the best.
Thank you.
Thank you, Mr. President.
Thanks to you. Nicolas, the last word.
Yeah. Tomás, I was wondering, just one small question. I was wondering what your actual parents are thinking about your algorithm of always changing parent and choosing them.
I don't think that they care too much, because they said to me that they are going to be viewing the meeting, but they are not going to understand what I'm going to talk about. So I think that is fine.
Okay. No, I don't have serious question. I think we discussed a lot already. I especially remember this long talk we had in Ireland, where we decided to walk to the conference, and it was I think 1 hour and a half or something like this.
Oh yeah, I remember it.
So yeah, it was a pleasure to work with you. I'm very impressed what you did, especially the last few months, because with the pandemic, it was, I think, very difficult for you to, as for everyone, to continue working. So we know that finishing a PhD is already something very hard. And so with the pandemic, in addition to that, you did a real great job to finish your PhD and to reach this level of the manuscript and the presentation. Something that I will just say one thing about the work, and something that I really liked is that we came up with a lot of hypotheses and things that we thought we will see in the implementation. And each time you got results, each time we discovered something that was unexpected.
That is true.
And at the same time, very interesting, but at the same time, it took some time to find out why it was a mistake or not a mistake, problem of the algorithm and stuff like this. So you really did an investigation, like you say during your presentation.
Well, that's the whole thing of the PhD, to do investigations, right?
Right. So that's all. Thank you.
Thank you, Nicolas.
Okay, thank you, everyone. So now the members of this committee will move to another meeting to deliberate, and we'll be back in this room in some minutes. So see you later.
So Thomas, stay connected and we'll join the meeting room that we used before, right?
All right, others. Perfect. Yes, no problem.
Thanks. So I'm back. I'm waiting for the whole committee to be back in the room.
I'm going to disconnect the microphone.
Are you guys can still hear me, right?
Yep, we can.
Yes? Okay, cool.
Antoine,
ok.
On est venu dans la même salle, nous, ouais. C'est plus simple.
Parfait. C'est magique.
T'as oublié ton masque.
Bravo.
Je suis pas malade.
Ah oui, je voyais pas Diego. Si, c'est bon. Ouais, tout le monde, ok. So, Thomas, I'm here to tell you about the report the committee agreed on. So, you presented your doctoral work in a clear and dynamic and comprehensive manner. The jury particularly appreciated the scientific methodology adopted and applied throughout your defense. After you introducing the issue of connected objects for industry, the candidate detailed his contributions around routing solutions for the low energy consumption networks. You made relevant you made relevant choices throughout your presentation, thus supplementing the elements present in your manuscript. In particular, you clearly presented your contributions related to the establishment of multipaths by using repo in order to meet the reliability and latency constraints imposed by the targeted applications. The jury wants to underline the difficulty of proposing original solutions in this active and dense field, and you were able to convince everyone that your experimental results were thorough, and you did that by appropriating several tools from the community. And at the end of your presentation, you answered with precision the many questions of the committee. And this moment allowed us to verify your scientific and technical knowledge, as well as your ability to take a step back from your subject. So for all these reasons, the unanimous jury awards you the rank of Doctor doctor from IMT Atlantique, Bretagne, Pays de la Loire. Félicitations.
Bravo.